Hi, welcome. This is CSC 480, Assignment 1, Modified 8 Tile. My name is Corey Glodick, and we'll jump right into running the program. Simple text interface, type in what you want, hit return. We'll go with breadth first search and easy first. Prints out the solution, step by step, showing the move, the cost, total cost, and the maximum depth. We'll do iterative deepening next. And we will go with the depth of 9, and we will go with medium. Same thing. Just hit that. A star 3 is next. And let's do medium. There we go. All of the agents that I implemented, including the extra credit, all resulted in solutions for all difficulty levels. I used, this is the main class, named it P node. For puzzle node, hard-coded for the goal state. It's got its constructor for hashing and string, return a boolean if it meets the goal. The main method for the heuristic implements uniform cost, best first, and A star 1 through 3. They use similar functionality, so I decided to put it all into one method. Now A star 3 I implemented with total cost plus the number of tiles out of place plus the Manhattan distance, and it did result in a better solution. Override for the comparators. Find children. Finds the location of tile 0, puts that in a 3x3 board. Finds any available moves and removes any that are illegal, as in if 0 tile was on an edge of the board. For each move, it'll iterate through, and it will create a new node based on the cost of the tile that's being moved and update the state. It will go through all the available moves and return all the available children. Find moves. And the solution. This is just returning the overall solution in a format that's easy to print out. Moving to breadth first search, utilized a queue for this one, set for the previously visited states, just called it history. Set under the hood for Python results or uses a hash table, significantly sped up the processing. Keeps track of the overall size of the queue, maximum size at any given time. Grab the node, discard it from the state, add the state to the history. Now find all the children. For each child that's in children, if it's not in history and it's not in the current queue, then it will check to see if it matches the goal. And if it doesn't, puts it on the queue, adds it to the queue state. All the implementations do return a dummy node if no solution is found. This is only applicable really for iterative deepening, but I figured I'd build that in. With depth first search, used a DQ, so it's first in, last out. Very similar to the breadth first, with the exception that I did not use queue checking. It seemed to increase the overall amount of time. And did not result in as good a solution as I would have liked. Iterative deepening, blending breadth first search and depth first search, it will iterate through each layer of depth. So at 0, depth first all the way to 0, obviously it returns and increments up to 1, and then continues to the max depth that was input, performing depth first search at each layer. Again, returns a dummy node if no solution is found. With uniform cost, best first, and A star 1 through 3, I used a priority queue heap to keep track of that and keep that sorted. Same thing with the set. I did use a dictionary to track what the priority of each node was in the heap, and use that to know its location, the priority, and update if need be. Very similar as the rest of them, cycle through, check, grab the H value, update as needed, return solution. Thank you.